been studying quadratics. You guys are getting familiar. There's three different forms of the equation. There's a graph called a parabola that goes with it, right? Um, and before we jump into this, I have to give you a little background. So we don't have a lot of background or a lot of time to go into it, but if you look at the history of numbers, like what when when people started using numbers, they didn't start off using square roots or fractions. They started off using 1, 2, 3, 4. So things they can count with their fingers, right? Integers. They didn't even have negative numbers. So things like negative numbers or square roots came in to history later on. And what introduced those things were trying to solve problems. So like if we had an equation like this, x plus 4 equals 2, and how do we solve that? Then we need something called a negative number, right, to solve for x. Or if we had something like x squared equals 2, what number squared equals 2? That created a need for what kind of number? The square root, okay? So the most recent kind of number came out of trying to solve equations as well, and solving this equation, x squared equals negative 1. Like what number squared equals negative 1? And mathematicians argued over this. Some said nothing, that's pointless. Others said, no, there should be a number that works for that. It's not pointless. And there's this debate going on. Eventually, one side convinced the other, and they said, well, let's call it, well, the square root of negative 1, which we'll say is I, or the imaginary number. Okay? And so that's what I is. I is the solution to this problem. What number squared equals negative 1? I. Okay, and still, when people started to use this, other mathematicians are like, what's the use? There's no application. And actually, at first, nobody found any applications, but over time, again, there's actually an imaginary number can actually impact real life, and it happens primarily in electrical engineering, which we don't have a lot of background for that, so we can't go into that. But just know that it isn't just something out there. It actually has some practical life impacting things. Okay, so I'm just introducing it to you because we're going to need it today. So for us, when we have the square root of a negative, so say the square root of negative 2, okay? In the past, how many have heard your teacher say, that means there's no solution? Anybody ever heard that? And that's not really true. What they should have said is there's no real solution. That's true. But there's an imaginary solution, okay? And it would look like this. Never leave a negative underneath the square root. Instead, you remove that negative and you put an I out in front of the square root. So this would be equivalent to I root 2, okay? Or if I had the square root of negative 3, that would be what? I root 3. Okay, they mean the same thing. If you could simplify something like negative 12, so what's the square root of 12? 2 root 3. But this has a negative, so you're going to use an I, and so the I is usually squeezed between the 2 and the root 3. So it comes after your integer value, but before the root, kind of the placement of it. So square root of negative 12 would be equivalent to 2I root 3. What if I had the square root of negative 4? 2I. What if I had the square root of negative 9? 3I. What if I had the square root of negative 16? Would you call me? You making fun of me because I wear glasses? Call me 4 eyes? Just joking. All right, so we're going to use that here. And we're going to start with number 25. Okay. So what can we do with 25? Find y-intercept. So plug in 0 for x and get -21, right? Because when you x squared would be 0, negative 6x would be 0. All you're left with is that 21. So 0, 21 is our y-intercept. Can we factor this? We come up with two numbers that multiply to 21 and add to negative 6. If we can, that's a much easier problem to deal with. Does it work? Okay, I'll trust you. So it doesn't work. So it does? Okay, so no factored form. So if it doesn't factor, then we need to get our vertex form. And this is when we start to use that new technique. And what we said to do is look just at the x squared minus 6x, and you want to change that into a perfect square. Now, do you remember a few days ago when we said standard form and vertex form will be the same if a certain thing happens? When's that true? When your linear term is not there, or when b is equal to 0 is another way to put that. Okay, so if you're missing that middle term, don't forget that, because that will come up again, and when you see that, you can always use that. Okay, but here it's not in the right form. Okay, so we need to get in the right form. X squared minus 6x. So what would be the perfect square that we want to create out of x squared minus 6x? X minus 3 squared. So what we did is we took the negative 6. If you cut that in half, that gives you the negative 3. And then to figure out what to add, you're going to take the negative 3 and square it. So negative 3 times negative 3 tells us what number we need to add to complete that square. So I need to add a plus 9. And so in this equation, I'm going to write y equals x squared minus 6x. I'm going to move the 21 over. So that's the same equation, but I need a plus 9. When I put that there, now the equations are not equal to each other. So I need to balance the equation by putting a minus 9 right there. Okay. So is the first equation the same as the second equation? Are they equal to each other? Yes. And I'm putting that plus 9 there so that now I can change the first three terms perfect square, x minus 3 squared. Negative 9 plus 21 is 12. And we've got it. So this is our vertex form. Okay. What would you do next? Find the roots or the vertex? Okay, we already know the vertex. What's the vertex? 312. What else do we know? Which is x equals 3. Okay. Okay, if we don't do any other work here, and we just, based on what we have here, what can you tell me about the graph? You can tell me the center. You can tell me the vertex. It's going which way? It's going up. So like it would look like this. So it has a maximum or a minimum? A minimum. So it's opening up, and what's the minimum value? So 312 is the vertex, so the lowest value is 12. It can't go lower than 12. It can go higher than 12. So what does that tell you about the x-intercepts? It's never going to hit the x-axis. It's not. Okay? Right? The x-axis is below that, and so this parabola is not going to cross our x-axis. And so there are no x-intercepts. So what do you think is going to happen when we try to solve for our x-intercepts? That's when we get imaginary answers. Okay? If you get a real answer, it will cross the x-axis. If you get an imaginary answer, that means, hey, this thing's not crossing the x-axis. Okay? On this xy, you cannot graph imaginary numbers, or we call them complex numbers, in your xy plane, because your x-axis and your y-axis are real number lines. There's nowhere to put an imaginary number on this. There is something called the complex plane where you can graph imaginary numbers, but we're not doing that, okay, right now. Yeah. We'll get there. But let's go after our roots. Let's go after, we know they're going to be imaginary, but let's find them. So we're going to take the x minus 3 squared plus 12, set that equal to 0, and solve for x. What's our first step for solving? Okay, so subtract 12. Second step, square root of both sides. Now careful, when you take the square root of the left side, you get x minus 3. When you take the square root of the right side, don't forget the plus or minus. And then it's going to be a square root. Make sure the negative goes underneath that square root with the 12. I've seen a lot of people say, oh, well, there's a plus or minus already, so I don't have to put the minus into there. You do, because that's what makes it imaginary, right? And then we already talked about simplifying square root of 12. And I'm going to add 3 to both sides. You get 2I root 3. Now that's your square root of negative 12. And so if we were to split this up, we get 2 values for x. One of them is 3 plus 2I root 3. And the other one's going to be 3 minus 2I root 3. And so our roots are going to be 3 plus 2I root 3, comma 0, and 3 minus 2I root 3, comma 0. So we can't use those for our graph because they're imaginary. We can use 0, 21, and we can use 3, 12. So now let's get to our graph. So we know it's not crossing the x-axis, so I'm going to make that x-axis really low. We know the center is happening at 3, so I'm going to shift the y-axis a little to the left because the middle is going to be at 3. Okay, so there's our middle. Our vertex is the lowest point at 12. And I'm going to reach a y-intercept at 21. So you can go by 2s or however you want. If the numbers get really big, maybe I'll demonstrate that now. So because you'll have some problems. Like look at the next one. You're going to have a y-intercept at 123. Okay. So if you get something like that, don't put 123 marks. Don't even mark the y-axis. Just do something like this. I'll demonstrate here. Here I could mark the y-axis. I could go up to 21. That's not a big deal. But 123, that's a little more, right? So you just put your vertex down and say that's at 312, right? So you're letting me know the location. And then 021, you say, okay, looks like it's right there. 021, and you just label it so then I know exactly where that's at. Okay. And then you don't have to put all the tallies on that y-axis. Once you get to big numbers, you're welcome to do that. So if we reflect 021 across the axis of symmetry, what's going to be over here? 621, good. And I want you to have 5 points when you're graphing. We only have 3. We need to come up with 2 more. So plug in something and keep it close to the center of your graph. So plug in a 2 would be great, or a 1 would be great. Doesn't matter. So plug in something. Tell me a point that that works. 2 what? I need to know the actual coordinate. Okay, what does y equal? I need the coordinate. I need the x and the y. So, I don't think so. Because 2, 1's going to be down here, and that's not going to, that's my lowest point. So 213? That makes sense to me. Okay, so 213, and then if we reflect that across the axis of symmetry, we'll get 413. So for those of you that are wondering, like, where's the 213 coming from? Ty, what did you do to get that? Okay, so if you say let's let x equal 2, and you plug 2 into the standard form, you get 2 squared minus 6 times 2 plus 21. You work that out, and that's where we're getting the 13 from. Okay. So we have our 5 points. So I'm going to put that here. So 0, 2, sorry, 0, 21, 2, 13, 3, 12, 4, 13, and 6, 21. Domain is all real numbers until we start to use a context. We're not using context yet. When we get to real world problems, we'll start to change that. The range, though, changes problem to problem here. Kaya, what's the range? Greater than or equal to 12. Okay, good. And then this graph is going to be increasing. Where, Tyler? Where's it increasing? Good. And decreasing when x is less than 3. All right. So again, your roots had no bearing on the graph at all, right? But we have this imaginary thing called roots. Now, in our little space down here at the bottom, I want us to include something that's going to be important for us. So up until this point, because we were working with real numbers, I told you that the x-intercepts, the roots, and the zeros were all the same thing, right? But now that we're talking about imaginary, they start to part ways. So x-intercepts need to be real numbers. So the problem we just did, didn't have any x-intercepts, right? Because it did not cross the x-axis. And so if I asked you what were my x-intercepts, you would not put 3 plus 2i root 3. You'd say there are none. Okay? But if I asked for roots or zeros, then you give me real or imaginary. The roots and zeros are both real or imaginary, okay? And if you have something like a real number plus an imaginary number, we call that a complex number. So roots and zeros can be complex. Okay. And so the answer we had in 25 we'd say that's a complex number because it has a real part, which is 3, and it has an imaginary part, which is 2i root 3. Just some language there, but key thing is this is where x-intercepts and roots and zeros start to part ways. One accepts the imaginary, one doesn't. Okay, so just keep in mind, like number 26 is asking for an x-intercept. So if you get imaginary roots, you're going to say, I don't have any x-intercepts. You're going to write none. Okay. All right, let's move on to yeah, let's do number 27. And I'm going to give you a 5-minute head start. Do everything you can in 5 minutes. Number 27. When we get to that point, feel free to ask questions. If you're not sure how to do something. Number 27, does it factor? No, doesn't factor. Y-intercept, you should be, if you plug in 0, you get 13. And then x squared plus 4x. I want to add something to this to complete the square. What do you guys end up adding? 4 or 2? So if we have x squared plus 4x, we're going to have to add a 4 in order to make a perfect square, x plus 2 squared. And half of 4 is going to be 2. That's what we find first. And if you square the 2, you end up with 4, because 2 times 2 is 4. So I need to add a 4, and then I'm going to subtract 4. Okay. And then I continue on and factor just the first 3 terms. And that becomes my x plus 2 squared. And then negative 4 plus 13 is going to be positive 9. So that's what you want to give for vertex form. X plus 2 squared plus 9. And so our vertex, you get negative 2, 9. Axis of symmetry is x negative 2. From there, we can find our x-intercepts by setting our equation equal to 0. Oops. And solving for x. But before we do any work, just based on what's on the screen here, can we tell if there will be any x-intercepts? Why? Well, so before I do any work, before I even find out there's imaginary numbers, there will be, but is there a way to find out I'm going to get imaginary numbers based on what's just here before I do any work? Yeah, Kaya? So you're thinking about this. What about this? Is the vertex a maximum or a minimum? Okay, it's a minimum because it opens up, and it opens up because A is positive. So what's the minimum value? 9. That means this parabola cannot go lower than 9. And in order to have an x-intercept, it has to go to 0, and it can't. And so I know it's not going to have an x-intercept just before even trying to solve. But I'm going to solve still because we're practicing our solving here. So x plus 2 squared is equal to negative 9. Take the square root of both sides. You get x plus 2 is equal to, don't forget, plus or minus square root of negative 9. Subtract 2 from both sides. And then the square root of negative 9 is 3i. So if I asked you for the roots or the zeros, you would give me negative 2 plus 3i and negative 2 minus 3i. But I'm not asking for the roots or zeros. I'm asking for the x-intercepts. And that's when the x-intercepts a bit different. Say there are none. Okay. Not going to cross the x-axis. So now let's sketch this graph. I'm going to make my x-axis low here because it's not going to even hit it. I'm going to move my y-axis a little bit to the right because the middle is going to be at -2. So here's the middle. And the lowest point is at -2,9. So I'm going to go up 1, 2, 3, 4, 5, 6, 7, 8, 9 right here. My y-intercept's at 13. So 10, 11, 12, 13 right there. If we reflect that across your axis of symmetry, where are we at? -4, 13. You need 2 more points. Can't use x-intercepts because we don't have any. So plug in another value. Did anybody plug in something? You plugged in -3. When you plug in x equals -3 into your equation, what do you get for y? 10. So -3, 10. And if we reflect that across the axis of symmetry, we get -1, 10. We have our 5 points. So how did you do in that process? Were you able to make some progress? If you got stuck, where did you get stuck? Plugging in numbers? Braden, what's our range going to be? Good job. Natalie, where's it increasing? Good. All right. So there it is. Question? All right, one more. Let's go to the next page. Let's do 30 together. Or would you rather me stop there and you do the 4? You want to do one together or not? Do one more? Do you some time to try it? How much time do we have left? We're out at 58. And it's 50 right now. I give like a 3-minute. I'll work 3 minutes while you're working 3 minutes, and then show. How about that? So you start and I'll start. Number 30.